Dear students, welcome to the next lecture of wireless communication. So today we will start a new topic called cellular wireless networks. Okay, so let's begin. So cellular networks, we all are using the cellular networks for our mobile phones that we all carry. Okay, so this was a revolutionary development in data communications and telecommunications. Okay, so and this is the foundation of the mobile wireless. So all the telephones, smartphones, tablets, wireless internet, wireless applications that we are using today are mostly supported by these cellular networks. Okay, we do have other wireless technologies like the WLAN or the other standards that you have studied so far, 802.15, Zigbee and other things. So they are also wireless technologies, but none of them support mobility. Okay, so when we talk about mobile wireless, we are basically talking about cellular networks. Okay, so again, WLANs, Zigbee, etc., they can provide mobility, but only to a very small extent. If you recall those Kvyat graphs that we showed some time back in one of your video lectures, then all other technologies you would see that score much less in terms of mobility, which is the main advantage of cellular networks. And cellular networks started with the 1G standards. That was the first generation of your cellular networks, which only provided analog voice communication. Then 2G came, which still used to carry voice, but then some text and data functionalities were introduced. 3G was the first with sufficient speeds for data networking, and 4G is the true broadband mobile data provider up to 1 gigabits per second. And 5G, we have also 5G today. So 5G again, it gives further enhanced data rates. Okay, and also more reliability. Okay, so as you can see, all these G's or the generations of cellular networks, they are really the enhancement in terms of technology and bandwidth of the previous generations. Okay, and we have 5G today, which is the best possible technology solution that we can have. And people are researching towards 6G also, so that again is a futuristic technology. So depending on the demands of the users, and depending on the advancement in the related technologies, we had all these generations of cellular networks. So let's look into the details of the cellular network. So the first thing is the organization of the network, which is done into several cells. Okay, so that's why the name cellular comes here, because each cell, so first the entire network is divided, or entire geographical area is divided into cells. Okay, and each cell is served by its own antenna, and also you have a base station that consists of several transmitters, receivers, control unit, and also the antennas. Okay, so you have a cell. You will see in the next slide that these cells are arranged like hexagons like this. Okay, so your entire geographical area is divided into cells like this, and each cell has its own base station with several antennas and several transmitters and receivers and a control unit. And we have band of frequencies that are allocated to these cells. Okay, and each cell operates on a distinct band of frequencies. The cells are set up such that the antennas of all neighbors are equidistant from each other. So that's why we are using the hexagonal pattern. Okay, we will come to this detail very soon in this lecture. Okay, so here we have actually. So so why you have this hexagonal geometry? So this is the hexagonal pattern that is adopted for cellular networks. So each of these hexagon determine a geographical area where you will have a base station in the center with transmitter, receivers and their antennas, and then the several users will be located in this cell, each one with their wireless mobile devices. It can be a phone, it can be a laptop, it can be anything, and they will connect to this base station. Okay, so why is this hexagon used rather than, let's say, a square pattern? You could have also gone with a square geometry where each cell is divided into a square with the base stations in the center. And the reason is that in case of your hexagonal geometry, let's consider this one. Okay, so this one has 6 neighbors, 1, 2, 3, 4, 5 and 6, and the antenna in the base station of this cell is equidistant from the antennas of all its neighbors. Okay, it doesn't happen in a square geometry. Okay, in the square geometry the corner antennas are at a greater distance than the sidewise antennas. Okay, and because of the equal distances, okay, the interference in signal because of these neighbors, okay, would be equal, okay, to the central base station, whereas in this case this won't be the case. So these antennas will be very strongly interfering because they are at a closer distance to this antenna compared to these antennas. Okay, and that would have an effect on the design of the network. Okay, so the idea is to have all the neighbors at equal distance from the central transmitting antenna. Similarly, when this antenna is under your concern, then this will also have 6 equidistant neighbors. Okay, 1, 2, 3, 4, 5 and 6, and then it will have interference or interferers equally spaced between the antenna that we are considering. So this is important, and this is why a cellular geometry is preferred. And also the surface area of a hexagon is higher than compared to a square. So with the hexagonal geometry you can cover a larger area with more effectivity. You can have more number of base stations that can serve the entire area. Okay, So that is also a possibility. And in terms of the users also, you can see, you know, um, so hexagonal geometry actually emulates, you know, the circular geometry very well. Okay, let's say if you have a hexagon that is close to a circular geometry, so all the users here, they have they are at a distance, okay, um, that are close. I mean, they are all the users are at an advantage in terms of accessing this base station. Okay, so let's say the maximum distance that an user could be from the base station is defined by the radius of this hexagon. Okay, but here in the circular geometry you can see that at a user at the corner of the circle is at a higher distance than a user at the sidewise. Okay, so this is a disadvantage as well. So for these several reasons, the hexagonal pattern is chosen. Okay, so now we will go through the frequency reuse concept. Okay, so in frequency reuse, basically, as you saw, we have hexagonal geometry. So adjacent hexagonal cells are assigned different frequencies to avoid interference or crosstalk. Okay, so let's imagine that you have this type of geometry as you saw. So let's say you have this type of geometry, and if this cell, let's say, is using a frequency range from let's say centered around f1. Okay, so let's imagine that this cell is using a spectrum that is centered around f1. Okay, and it's using all the frequencies that are centered around f1. Okay, all these different frequencies that are centered around f1. Now if the adjacent cell, if that also uses the same frequency range centered around f1, then there will be a lot of interference between these two adjacent cells. Okay, to avoid that, the adjacent cells can be allocated over a frequency range that are centered around f2. Okay, so and then this can have f3 and so on, f4, f5. Okay, let's say this is f1. Okay, and then you have f2, f3, f4, f5, f6 and f7 along the neighbors. Then the same frequency can be reused. Let's say for this one you can use f1 again here, because this cell is not an immediate neighbor of this cell. Okay, the immediate neighbors are these 6. Okay, so you can reuse the same frequency f1. Okay, here. Okay, so that's the concept of frequency reuse that we are talking about here. So the objective is to reuse the frequency in nearby cells. So you set n different frequencies for a cluster of n adjacent cells. So here we have a cluster of, let's say, 1 and then the 6 of its neighbors. So 1, 2, 3, 4, 5, 6, 7. So you have 7. You can have an n that is equal to 7, and then you use f1 to f7, let's say, for this particular cluster, okay, and then you can use these frequencies for a different cluster, okay, and the transmission power is controlled to limit the power at that frequency escaping to adjacent cells. The issue is to determine how many cells must intervene between two cells using the same frequency. So what could be a number n, okay, it can be any pattern. So here we have shown an example of, n equal to 7. You can have any power, and that is determined by how much you can control your transmission power, so that you can limit the power that is escaping to adjacent cells, and how many cells must intervene between two cells using the same frequency. Okay, so these are different design parameters that you can use to determine what will be this number n. So there is a trade-off between this n and how many frequencies you have to choose from, and what are these parameters to determine the final n that we can have. So in general we can have n equal to 4, okay, so you can have a pattern like this, okay, so you can have a pattern like this, and then you can number the cells as 1, 2, 3, 4, so you can have n equal to 4, and then this pattern is repeated, okay. So so when the cell that is numbered 1, it can find another cell that is number 1, okay, at a circle with radius capital D, okay. So D is another parameter you will see for this type of cellular network design. So we have N and we have D. There are several other parameters, we will all learn about them eventually. So at a circle of radius D, you can find another cell which has the number 1, and then the pattern for n equal to 4 is repeated again, the same pattern. So you have 1 here, then again 2, 3 and 4, and you can see that this pattern of n equal to 4 is repeated, and each cell that is numbered 1 will get a frequency f1, and that cell which is numbered 1 can use a certain band of frequencies that is centered around f1, like this, okay. And then the cell 2 will use f2, 3 will use f3, 4 will use, let's say, f4, so that they don't interfere between themselves. And then this pattern can be repeated, so then this 1 will again use f1, this 2 will use f2, and so on. And you can see that this one is separated from this one by another cell here, so the chances of interference is less, okay. If you increase n, then you will have a better scenario. So you can see if you increase n to 7, then the pattern 1 is repeated at a circle of radius d, but this is approximately 2 cells away, okay. So and then the chances of interference between these two cells which are numbered 1 are even low. So when you increase n, you are actually decreasing the interference, okay. So and then the reuse of frequencies will be done. So this one which is appearing here, 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 will be able to reuse the frequencies that is used by this cell, but then the chances of interference is reduced because they have many layers in between. Okay, you can have n equal to 19, okay, and you can have different n's. So all these numbers, n equal to 4, 7, 19, these just doesn't come randomly. Okay, these have a relationship that is associated with the hexagonal geometry of the cells, and these relationships follow this pattern. Okay, so let's first go through the different parameters. So D, as you saw, this is the minimum distance between centers of cells that use the same frequency band. Okay, so sometimes called co-channels. Okay, so for n equal to 19, let's say this is the cell number 1. Okay, and then after using a pattern of 19 cells, you can find another cell number 1, which is here, and this is at a radius d from the center of this. Okay, so this is your capital D. Okay, here also you have this circle of radius capital D. Here also you have this circle with radius capital D. So D is the minimum distance between the centers of cells that use the same frequency band. R is the radius of a single cell. So if you have a cell, hexagonal cell like this, this distance is your R. Okay. D is the distance between the centers of adjacent cells. Okay. So D is actually square root of 3R. Okay. So this comes from the fact that you have, let's imagine 2 hexagonal cells. Okay, so this distance is R, this distance is also R. Okay, let me erase. Okay, let's say let's look at it into it differently. So let's say this distance is R. Okay, and this distance is also R. Okay, and D is the distance between cells or centers of adjacent cells. So this distance is D actually. Okay, so now if you look into the geometry of the hexagon, so this triangle, this angle is basically 60 degree, because you are dividing the center, you are dividing the hexagon into 6 equilateral triangles, and all of them has a 60 degree angle at the center, so that the total angle is 360 degree. So if this is total 60 degree, then half of it, this particular angle, okay, is 30 degree. Okay. Now this distance from the center to the edge is basically D by 2. Okay. If the entire distance is D, then up to this much is D by 2. Okay. So you can write D by 2 is equal to R, okay, R cosine of 30 degree. Okay. So D by 2 is R cosine 30 degree, and cosine 30 degree is square root of 3 by 2. Okay. So this is square root of 3R by 2. So therefore your D is actually square root of 3 times R. Okay. Now N is the number of cells in a repetitious pattern which you just saw. Okay. from the previous 3 slides. So this is termed as the reuse factor. So in case of an hexagonal cell, n will follow this rule, okay, I square plus j square plus I cross j, okay. And I and j are integers which can take values between 0, 1, 2, 3, etc. And because of this, n can take value 1, 3, 4, 7, 9, 12, 13, 16, 19, 21 and so on, okay. So that's why the examples that I gave you was taking values n equal to 19, n equal to 7 or n equal to 4. So n can take only certain specific values that is determined by this equation, okay. And how this equation is derived, okay, we can do a little more mathematical exercise to find out how this equation is derived. So I and j are nothing but like what are the distances, okay, of the adjacent cells from a chosen cell. So let's say this is my chosen cell, okay. So this cell is at a distance j equal to 1. So this is the first adjacent cell of the chosen cell. This cell is at a distance, okay. So imagine that this distance is d, okay, between two adjacent cells, okay. This distance is at a distance 2d, okay, and this distance is d. So this is basically j times d where j equal to 1, and this is I times d where I equal to 2, okay. So depending on this geometry, okay, you have this I and j defined, okay, and let's say if r is the cell radius and d is the distance between the centers of the nearest co-channel, okay, so these parameters we have already defined, okay. Let's say d, okay, let's say d is the distance between the adjacent cells. Then you can have this type of pattern, okay. Let's say we have a frequency reuse pattern of, let's say, n equal to 6, okay. So this type of, n equal to 7. So you have this type of a pattern which is repeated here, okay. So you have you call the center cell as A, okay. Then you have the same corresponding cell which is here, A, and A, okay. If you draw a large hexagon that connects the centers of these co-channel cells, okay, then the radius of this large hexagon is d, okay, and the radius of the small hexagons are r, okay, and the adjacent cell distances are called alpha here, which is same as d that we introduced previously, okay. So let's assume that alpha, d, whatever, these are same, okay, alpha equal to small d, okay. So with this geometry in mind, the area of a small hexagon is proportional to r square. So you have k times r square where k is a constant. The area of the large hexagon is k times d square, okay, where the proportionality constant is same, because this is something that is related to the geometry of a hexagon. So if the hexagon radius is r, then the area is k times r square. If the hexagon radius is d, then the area is k times d square. Okay. So this large hexagon area is k times d square, and the small hexagon area is k times r square. Okay. So now from the geometry of the triangle, so this is again, this is d square. So d square is 3r square. We have established this before. We have established this, that d equal to square root of 3r. So d square is 3r square. I mean small d square. Capital D square, okay, if you look into this geometry, okay, so capital D square, this distance is capital D. Okay, let's say if you find the nearest co-channel cell by walking, let's say I cells towards north and J cells towards west. Okay, so this is your I and then J. So in other words, this distance is your I times D. Okay, this distance is I times D, and this distance is J times D, as I just showed here. This distance for this example is 2 times D, and this distance is just D, where I equal to 2 and J equal to 1. Okay, so this triangle, if you consider this triangle, then this distance is capital D. Okay, this distance is I times small d, and this distance is J times small d. Okay, I times small d and J times small d, and this angle is 120 degrees. Okay, so apply this for the triangle. This is the triangle identity. So you have I square d square J square d square minus 2ij d square equal to times cosine of 120 degree. Okay, so now you will get capital D square is equal to small d square times I square plus ij plus j square. Okay, small d square is 3 times r square. So therefore from here you can say and again, okay, if you go back here, d by r again is basically square root of 3n. Okay, so this is again I will prove this later in a discussion class maybe. I leave it to you as an exercise that d by r is square root of 3 times n. Okay, you can find it out by looking into the internet. Okay, I will also prove it in a later discussion class. Right now I leave it as an exercise. So I have established that d by r is basically d by r is square root of 3 times I square plus ij plus j square, right from here. And if you believe me right now that d by r is also square root of 3n, d by r equal to square root of 3, and this part I leave it to you as an exercise to prove. If you can't, we will discuss this in a discussion class later. So if you believe me for now that d by r is also this, then from here we can directly get that n is equal to I square plus j square plus ij, where I and j are integers. Okay, so this establishes this fact that n can only take these values. Okay, so the reuse factor n can take values I square plus j square plus ij, where I and j are integers. So moving on, we will solve some examples where we will be using this relation. But right now I want to just move on. So approaches to cope with the increasing capacity. Okay, so you just saw that you can only use certain set of frequencies, right, for a channel, for a cell. So if you are using frequency reuse, then you can use like depending on the reuse factor, you can use certain set of frequencies. Okay, you can have increased reuse factor, okay, and you can use more number of frequencies, but then you are basically limited in your design by the amount of reuse factor that you can have, and the number of frequencies that you can use, and the reuse factor n that you can have depends on how much interference that you can have. So this is also limited by transmission power and how much interference you can accept. So your n is limited by how much signal power you can have, how much interference power you can tolerate, and how many frequencies you have for your design. Okay, so the capacity of the system that you can use is limited by all these parameters. Okay, but then you have so many users within a cell, so you will need more capacity. Okay, so and how to cope with that increasing capacity. Okay, so you can add new channels, so you can add more frequencies. Basically, you can borrow frequencies, so you can use the frequencies from the adjacent cells. Okay, if your adjacent cells are not using their stipulated set of frequencies, okay, you can use those frequencies. Okay, so let's say you have a reuse factor of n, so you can use f1 to fn. Okay, and these f1 are basically the center frequencies. So you are basically using a band of frequencies that are centered around, let's say, f1. Then you are using a band of frequencies that are centered around f2. You are using a band of frequencies that are centered around fn, let's say. So let's say this cell is using a band of frequencies centered around f1, and this cell is using f2. Okay, because this is its immediate neighbor, and this has to use a separate band of frequencies to avoid interference. Now let's say this cell is not using all the frequencies that are in this band f2. Okay, because it doesn't need to. This has less number of users, let's say, but this cell is very congested, lot of users are there in this cell, so it can borrow some frequencies from this cell. Okay, so that is what is frequency borrowing. Okay, You can have cell splitting. So cells in areas of high usage can be split into smaller cells. Okay, we will we will get into this concept right now in a separate slide. What is cell splitting? We can also have cell sectoring. So cells are divided into a number of wedge shaped sectors, each with their own set of channels. I will also get to this concept in the next slide. We can have network densification. So we can have more cells um, and frequency reuse. So we can have smaller cells. We can divide the same area with very large number of cells, or you can have more number of cells by having very small cells, and then we can have more frequency reuse if we have more small cells. Okay, so we can have micro cells, and we can also have femto cells. Okay, so these are some of the concepts that are used in more advanced cellular network generations like 4G and 5G. We can have other techniques like interference coordination. We can use intercell interference coordination. We can use coordinated multipoint transmission. So these techniques we will discuss towards the latter half of this module, when we will study 4G, etc. So right now let's just focus on cell splitting and cell sectoring. Okay, so this is cell splitting. Okay, you can split a cell into multiple areas. So cells in areas of high usage can be split into smaller cells. So that's what is happening. So these larger cells can be split into smaller cells like this. Okay, and then each of these smaller cells can use a different set of frequencies. So the large usage areas can be split into small cells with their own allocation of frequencies. Okay, and how this splitting or sectoring, let's say, increases the capacity, we will study those in a later class. Okay, we will do some solved examples, we will do some numerical examples where you will be able to appreciate the effect of splitting and sectoring, okay, to have enhanced capacity. So in case of sectoring, we can have a single cell like this with a omnidirectional antenna that is radiating power in all directions like this, or we can have a 120-degree sectoring where we have an antenna that has directionality across these three directions. So we can have an antenna radiation pattern that would look like this. It can have three main lobes that are directed across these three sectors, which are 120-degree in this angle, in the central angle that it makes. You can have 60-degree sectors also. You can have 6 sectors like this, where the central angle is 60-degree, and then you can have a directional antenna which has 6 lobes like this. Okay, and then you can have directional antennas across these separate sectors to have very strong signal power and then cancel the effect of interference, okay, from these adjacent sectors. So this is called sectoring. We will study more about this, I promise you. We will do some mathematical exercises to appreciate all these concepts, whatever we studied so far. Okay. Um, so talking about mathematics, we have some of the concepts right here. Okay. So if the let's say if the pattern consists of n cells and each cell is assigned the same number of frequencies, each cell can have k by n frequencies, where k is the total number of frequencies allotted to the system. Okay. So for example, there is a system called AMPS. Okay, this is a standard for cellular communication. So in that case, k is 395. So we have 395 frequencies overall to use. And if you set your n equal to 7, which is the smallest pattern that can provide sufficient isolation between two uses of the same frequency, then you can have 395 by 7, which is sorry 5, so roughly 57. Okay. If you consider to work with the lower bound, okay, if you work with the floor of this, floor of this, then you will get 57. Okay. So you can have 57 frequencies per cell on the average. Okay. So if we have a reuse pattern of 7, okay, then you can have each of these cells can use 57 frequencies. Okay. So if you have 395, and if you divide this into 7 bands, then each band has like F1, F2 to F57. Okay. So the center frequency of this band can be, let's say F1 to F57, and the central frequency can be somewhere in middle. Let's say F28 is the central frequency. Then you can have another band from F58 to F115. Okay. And you can have the central frequency around F86 and so on. So you can use all these 395 frequencies, and each of this cell gets, so let's say this cell gets F1 to F57, this one gets F58 to F115, okay, and so on. So you can have different frequencies in these different frequency slots, and you can say that this is your frequency band 1, this is your frequency band 2, this is your frequency band 3, and so on. And then you can get this reuse factor 1, this co-channel here. Okay. So this will be repeated again here with a certain separation between the two co-channels, and then you can reduce the effect of interference. So here is an example again. Assume a system of 32 cells with a cell radius of 1.6 kilometer. A total of 32 cells, a total frequency bandwidth that supports 336 traffic channels. And the reuse factor is equal to n equal to 7. So if there are 32 total cells, what geographic area is covered, how many channels are there per cell, and what is the total number of concurrent calls that can be handled and then you have to repeat uh, for a cell radius of 0.8 kilometer and 128 cells. So let us look into the problem closely. So first of all, if you look into the plan that is given on the left of your screen, which is this one, or case A, um, then you will see that for this case you have 1.6 is the cell radius. So if you look from this side, so this distance, this end-to-end distance is about 11 times 1.6, because if you see that if the radius is 1.6, then this distance is twice of 1.6. okay, and then this part is just 1.6. again you have twice 1.6, so 2 plus 1 plus 2 plus 1, again you have 2, then 1, and then again you have 2. So if you add this, then you will get 11 times the radius r, so that is the width. okay, so this is 17.6 kilometer. Similarly, if you look from bottom to top, then the total distance for a single cell is basically square root of 3 times r, the radius. okay, and then you have 1, 2, 3, 4 and 5 cells, so that height is 5 times square root of 3 times 1.6, so this much kilometer. okay, so in that way you can get the total area of the entire plan. So in that case you will see that the total area is basically 17.6 into 13.9. okay, this many square kilometer. okay, so you can calculate the area in this way. Also you can calculate, let's say if your radius is 1.6, then you can use this formula for one particular cell. okay, so the area of one cell will be given by okay, so in that case you will get with 1.6 kilometer radius, you will get this area as 6.65, and then for a total of 32 cells the total area could be 32 times 6.65. okay, so you can calculate in that way also. Now the main thing is the next part. So for n equal to 7, the number of channels per cell. okay, so you have 336 traffic channels. okay, so for a reuse factor of n equal to 7, the number of channels per cell is 336 by 7. okay, so that is equal to 48. So you can have 48 channels for each cell. So each of this cell can have 48 channels, since you are using a reuse pattern of 7. So if each cell uses 48 channels, then the total capacity of this 32 cell system is 32 times 48, that is the number of channels each cell can support because of this reuse factor 7. So this will give you a total of 1536 channels. So for now let's look into the, so this is for part A. okay, this layout. So you have 1536 channels. Now if you repeat the same calculations for this layout, then you will get the total area. If you use the same logic and calculation, you will get the total area to be equal to 213 square kilometer. Okay, just check yourself, apply the numbers that are given for this particular layout, and then again you have 48 channels per cell, because you are using the same reuse factor n equal to 7 for this case also. But then here you have 128 cells, so in that case the total capacity will be 128 times 48, so this will be 6144. Okay, so you can see that using the same reuse factor, okay, and more or less the same area, so you can see that this is like 13.9 kilometer of height and almost 17 kilometer of length. This one is 17.6, so almost with the same geographical area. Okay, you know, and the total area in this case was also 213, by the way, so almost the same area, 213 square kilometer, but you are applying two different layouts or two different design methodologies. So you are having in this case 32 cells of radius 1.6 kilometer each. Here you have 128 cells of radius 0.8 kilometer, but with this plan your total capacity is getting enhanced, so you have same total area for both cases. Okay, you have the same reuse factor for both cases, but by having more number of cells of lesser area, you can have the total channel capacity of the system increase to 6144 as compared to 1536. Okay, so again I repeat, for same, let's say for same area, same reuse factor, if you are having more cells, then you are getting more capacity. Okay, so this is the underlying message of this example. So you have the same total area, 213 square kilometer, you have the same reuse factor, but you are dividing the area either into 32 cells with larger areas or 128 cells with smaller areas, and then the 128 cell with smaller area is giving you an advantage in terms of the total capacity. Okay, so we will do more of this type of cellular network planning examples later in some tutorial, but let's now for the time being move on with the other concepts here. So so coming to the cellular system terms, so we have a base station. So this term most of you are already familiar with, I guess, because you must have heard about this as an user of the cellular system. Okay, so you have a base station. This includes an antenna, a controller, and a number of receivers. Then you have the mobile telecommunication switching office or MTSO, which connects calls between mobile units. And then two types of channels are available between mobile unit and base station. So you can have either control channels, which are used to exchange the information having to do with setting up and maintaining calls. So this is basically control information, and those control information are communicated between the mobile unit and the base station using the control channels. And then you have the traffic channels, which actually carry the information bearing data, that can be voice or the data connection between the users. So this is the pictorial overview of a cellular system. So as I said, you have these base stations. Okay, the base stations are controlled by the base station controller, and then you have the mobile telecommunication switching office or MTSO, that connects your base stations with the rest of the internet or the public telecommunication switching network. So this is basically your landline. Okay, this is the landline network that you have. So you can make phone calls between your landline phone and your mobile phone. So this MTSO takes care of this connectivity between the landline network and the mobile network. And of course, MTSO also connects your mobile phones and other mobile devices to the internet. So there are several steps in an MTSO controlled call between the mobile users. So these are the steps. So you have the mobile unit initialization, then you have mobile originated call, you have paging, then the call is accepted, the call goes on, and then if required there is a handoff. Okay, so in the next slide I will explain these steps with a diagram. So let's say you have your mobile unit is within this car and you want to communicate with another mobile unit inside this car. So the mobile unit will be monitoring for the strongest signal. So whatever are the nearby base stations, it will look for those and try to monitor for the strongest signal. And let's say this one provides the mobile unit with the strongest signal, so it will be connected to this base station, and this base station will send a request for connection to the MTSO. Okay, like this. Then after receiving the request for connection, the MTSO will send paging signals to all the base stations that is served by the MTSO. So in a geographical area, there will be multiple base stations that are served by one MTSO. So the MTSO will send paging signals to all the base stations. Okay, and the purpose for sending this paging signal is to find out the destination base station where your call will be terminated. So essentially you are trying to connect from this mobile unit to this mobile unit. So the MTSO, after receiving this request for connection, sends paging signals to all the base stations in the area. Okay, and then this destination base station, after receiving the paging signal, will understand that there is a call that needs to be accepted, which is originated by this base station. So the call is accepted in this phase. Okay, phase D. The other base stations will ignore the paging signals. Only this base station will respond and the call will be accepted. And then the call goes on between these two base stations which are serving the respective mobile units. Okay. And then let's say this car changes its position and moves to this cellular region and closer to this base station. Okay, so in that case the call will be handed off from this base station to this base station. So handoff is also a part of the procedure between an ongoing call. So whenever there is a movement for the mobile unit during the ongoing call, there will be a handoff from one base station to another base station. So these are the additional functions in an MTSO controlled call. So you can have call blocking, you can have call termination, call drop, and also you can have calls to and from fixed and mobile and remote mobile subscribers. So as you all know, you have also studied previously in this module that there are some issues related to the radio wave propagation. So those will affect the calls in a mobile cellular network as well. So there will be fading for sure, and the signal strength must be strong enough between base station and mobile unit to maintain signal quality at the receiver. Okay. So you have by now studied both in your wireless communication and digital communication the importance of the signal to noise ratio and also the channel capacity. So so the signal quality has to be good enough or strong enough to maintain a good signal to noise ratio to enhance the channel capacity. And it must not be again so strong as to create too much co-channel interference with channels in another cell using the same frequency band. So there is a trade-off here, as you can see. Okay. So the signal power should be high enough to maintain a good signal to noise ratio, but it should not be again too strong so that it creates interference for the other neighboring cells. Okay. So that is important, and then the effect of fading is also there. The signal propagation effects may disrupt the signal and cause errors. Okay. So so the mobile radio propagation effects can be mathematically modeled using a path loss model, but this is not the only effect that happens during the mobile radio propagation. Path loss is mainly the loss or the attenuation that happens, but there are other effects as well due to fading. But let's focus on the path loss for now. So the path loss can be given by this formula here. So you can see that the path loss is dependent on FC, the carrier frequency in megahertz. The path loss is also dependent on the height of the transmitting antenna. It is dependent on the height of the receiving antenna and also the distance d between the two antennas. Okay. So there is a function a of HR, where HR is the height of the receiving antenna. So this is a correction factor for mobile unit antenna height. Okay, and this is given again by different expressions for different environments. So for example, a small or medium sized city has this correction factor which is given by this. For a large city, the correction factor changes, and that too again for different carrier frequencies. Okay, so you have again for a suburban area, you have the path loss defined as the function of a path loss in an urban area minus these factors. Okay, again for an open area, or let's say a very remote rural area, the path loss is again given by the path loss of an urban area minus all these factors. Okay, so the basic idea is that the path loss varies depending on the environment. If it is a urban area where there are a lot of buildings, lot of people moving around, lot of reflection, interference, lot of diffraction, all these things, the path loss follows a different model compared to, let's say, a suburban or a rural area where you have less number of obstacles, less number of buildings. So in that case the path loss varies differently, and you have all these formulas that gives you how the path loss can be adjusted depending on the environment. Okay, so moving on, let's see an example to be able to appreciate this path loss dependency on the environment. So let's say if you have FC equal to 900 megahertz, the transmitting antenna height of 40 meter, the receiving antenna height of 5 meter, and the distance between the two antennas being 10 kilometer, what would be the path loss for a medium sized city? So for a medium sized city, according to the formula given in the previous slide, you have this adjustment factor. So you calculate this adjustment factor based on the values given here. So finally you calculate the path loss using the path loss formula, and you get 150 dB of path loss for a 10 kilometer distance. So you can see that 150 dB is quite high a loss. So when you go 10 kilometer in a medium sized city from the transmitting antenna, your signal is very poor. Okay, so 150 dB means 10 to the power 15 almost. So this means your received signal PR falls by 10 to the power 15 times of the transmitting signal. Okay, so this is quite a high loss. Okay, so so you can see that you in a medium sized city you cannot probably move 10 kilometer away from your transmitting antenna. So you may need more base stations within this 10 kilometer distance to get a good signal quality. So next we will move to the concept of handoff. Okay, so before actually diving into the concept of handoff, let's see what are the performance metrics related to handoff. Okay, so first you have the cell blocking probability. Okay, so this is the probability of a new call being blocked. Then you have the call dropping probability. This is the probability that a call is terminated due to a handoff. Call completion probability is the probability that an admitted call is not dropped before it terminates. And the probability of unsuccessful handoff is the probability that a handoff is executed while the reception conditions are inadequate. Okay. We have more performance metrics for handoff. So the handoff blocking probability is the probability that a handoff cannot be successfully completed. Then we have handoff probability, which is the probability that a handoff occurs before call termination. The rate of handoff is the number of handoffs per minute time. Interruption duration is the duration of time during a handoff in which a mobile is not connected to either base station. And then handoff delay is the distance the mobile moves from the point at which the handoff should occur to the point at which it does occur. Okay. So there are different metrics associated with handoff that you just saw. So there are also different strategies used to determine the instant of handoff. Okay. So these strategies are given here. So you can have the relative signal strength. You can have relative signal strength with threshold. You can have relative signal strength with hysteresis. You can have relative signal strength with hysteresis and threshold. And finally, you can have different prediction techniques. Okay. So let me go through these strategies and explain you a little more about this in this slide. Okay. So handoff between two cells, okay, happens when you are moving away from one cell and moving close to another cell. Okay, so let's imagine there are two cells here. Okay, so there you have this one with the base station A and this one with the base station B. Okay, and you are moving from here to here. Okay, so this is the picture here that gives you the relative signal strengths. Okay, so let's say base station A is here and base station B is here according to this cellular pattern. And when you move away from base station A, let's say the signal strength due to base station A falls with distance according to this curve. Okay, and when you move close to base station B, the signal strength goes up. Okay, or in other words, if you move from this direction to this direction away from base station B, then your signal strength for base station B goes low according to this curve. Okay, so now let's say you are moving in this car from base station A to base station B. So the first strategy that you saw in the previous slide was called relative signal strength. Okay, so that means when you are moving and your relative signal strength compared to base station A falls below the relative signal strength to B, then your handoff is initiated, and that point is this point. Okay, here the two curves cross, and when you move further away from this point, the relative signal strength due to A is lower than B. Okay, so this is the curve for B and this is the curve for A. So your relative signal strength falls below as you move to your right from this point. So this is the point denoted by L1, or this is the distance actually from base station A where your handoff can be initiated if you are following the strategy of relative signal strength. Okay, if you are following this strategy, then your handoff will be initiated at this length L1. Okay, now the second strategy was relative signal strength with threshold. So you can set a threshold like this. So threshold 1, okay, threshold 2, threshold 3. So if you want to follow the second strategy, which is relative signal strength with threshold, then you initiate the handoff when your relative signal strength falls below a threshold. Okay. Now, depending on how you choose your threshold, okay, your distance where the handoff is initiated will change. So let's say if your relative signal strength falls below a threshold and your threshold is this threshold 1, then your handoff will be initiated at this distance. Okay. So this distance is too close to the base station A. Okay, you don't want that. Okay, because here if you do the handoff, the signal strength due to B is very low. Okay, so you might not get a good signal quality. So if you use your threshold as this threshold 2, then if your signal quality is below this threshold, wherever that point is, let's say this point, okay, so your signal quality falls below this threshold at this point, okay, at L2, okay, at the distance L2 from base station A. Okay, so your handoff might be initiated at this distance L2. If you choose your threshold further low, let's say threshold 3, then your handoff might be initiated at a distance L4. Okay, and this is too close to base station B. Okay, so this may not be again suggested. So you have to choose your threshold in a way that your handoff is initiated somewhat in between the boundary of these two cells, right? You cannot have a handoff very close to your base station A or a handoff very close to base station B. You have to do a handoff somewhat at the boundary, equidistant from these two base stations. So you have to choose your threshold in an intelligent way. So maybe this threshold 2 is a good threshold because your handoff will be happening here at L2, somewhat in between the two base stations. Okay, so this is your relative signal strength with threshold. Now we can also choose relative signal strength with hysteresis. So what is that? So this means, let's say you choose a constant margin of H. Okay, you choose a constant margin of H, and you decide that if your signal strength, if your relative signal strength is less than, let's say your relative signal strength of A is less than B by a margin H, then you initiate a handoff. So according to this figure, the relative signal strength due to A is less than B by a margin H at this point. Okay, so this is the point where you should initiate your handoff. This is the distance L3. Okay, so the difference between the relative signal strength and relative signal strength with hysteresis is that if you choose your handoff based on the relative signal strength, then your handoff will occur here, because the signal strength of A relative to B starts getting lower after this point. If you choose relative signal strength with hysteresis, then your signal strength of A starts getting lower than B by a margin H at this point. Okay, so the handoff will be initiated at this point. Okay, so this is the hysteresis mechanism actually. Okay, so you have learned about hysteresis probably in electromagnetism. Okay, in electromagnetism. Okay, so in electromagnetism, when you are applying a electric current, okay, when you are increasing your electric current, let's say this is your current I and this is your magnetic field, then if you increase your electric current, your magnetic field increases, but when you decrease the electric current, the decrease doesn't follow the same path. Okay, so it decreases like this. Okay, and this phenomenon is called hysteresis. Okay, the same concept is applied here. So when you are moving from, let's say, A to B, okay, so this is your direction of A to B. Okay, so here you are measuring the relative signal strength, okay, PB minus PA. Okay, and when your PB minus PA, okay, so PB minus PA falls below value H, okay, then you are handing off to B. Okay, when your PB minus PA is greater than minus H, then you are handing off to A. Okay, so this is a similar hysteresis curve that is happening here in case of the current versus magnetic field curve. Okay, so you are following a similar type of hysteresis curve. Okay, so so your x-axis in this case is your relative signal strength, PB minus PA, and the y-axis is the assignment to a particular base station. Okay, so this is relative signal strength with hysteresis. Okay, and then you can also have relative signal strength with hysteresis and threshold. Okay, so you can have, let's say, you can apply some threshold, let's say threshold 2, and you can say if my relative signal strength falls below B with a margin H and also below a threshold TH2, then I can have my handoff at this point. Okay, so this point gives me the relative signal strength of A minus B, which is below this hysteresis margin H and also below this threshold. Okay, so this will be the point. Or if you choose threshold 3, then the relative signal strength of A is below a margin H as well as below this threshold, so your handoff will be initiated at L4, let's say. So you can have different types of strategies. You can choose the relative signal strength, you can choose relative signal strength with threshold, you can choose relative signal strength with hysteresis, you can also choose relative signal strength with hysteresis and threshold. And then you can have a totally different technique called prediction techniques, where you can use some intelligent agents and you can use some prediction algorithms, some machine learning algorithms to predict the instance as well as the relative distance of handoff based on different factors like the signal qualities and the mobility, etc. Okay, so this is a different technique that can use everything here. Okay, and some extra information, some extra data that is generated by previous handoff decisions. Okay, so you can use historical data of all the previous handoffs and then you can devise your own prediction models using machine learning algorithms. So so you need to have power control when you are using, you know, this cellular networks. Okay, and the reasons to include this dynamic power control in a cellular system is that the received power must be sufficiently above the background noise for effective communication. At the same time, it is desirable to minimize power in the transmitted signal from the mobile. Okay, so this is important to reduce co-channel interference, and then because of health concerns as well, and to save battery power. When we will study spread spectrum systems using CDMA, you will see that it's necessary to equalize the received power level from all mobile units at the base stations. So for all these things, you need power control. And then there are two types of power control: open loop power control versus closed loop power control. So in the open loop power control, it depends solely on the mobile unit, so there is no feedback from the base station, and it is not as accurate as closed loop because of this no feedback. Okay, but it can react quicker to fluctuations in signal strength because it doesn't need to wait for a feedback from the base station. In case of closed loop power control, it adjusts the signal strength in reverse channel based on the metric of performance, and the base station makes power adjustment decisions and communicates to the mobile on the control channel. Okay, so you have a feedback control system that is in action in case of your closed loop power control. Next, we will move to traffic engineering. So as you have seen in case of your car and bus traffic, let's say in case of your road networks, you can also plan and control your mobile telephone networks so that it can support a certain amount of calls, okay, or traffic. So this traffic engineering term is used a lot in telecom network design, and that has been borrowed directly from the road network. Okay, so when you say traffic in a road network, you mean the cars and buses and the different vehicles on the roads. Okay, in the same way, for a telecom network, you can use this terminology for the data traffic that is flowing through the different links of the network. Okay, so we will look into the concepts of traffic engineering for a cellular mobile network. Okay, so ideally, available channels would equal number of subscribers active at one time. Okay, but in practice this is not feasible. Okay, because there are a lot of subscribers that are using the system. Okay, and you cannot have as many channels as the number of subscribers. Okay, so in general, you have less number of channels as the subscribers, and the subscribers use these channels statistically, and that's where your concepts of traffic engineering come in. Okay, so for n simultaneous user capacity and L subscribers, let's say, if your L is less than n, okay, this is a non-blocking system. So if you have less number of subscribers compared to the total capacity, then all the subscribers can be accommodated and you don't have any call blocking. Okay, however, if your L is greater than n, which is the practical case, okay, this is the practical case for all telecom system. Okay. In that case, you will have some blocking when lot of subscribers are trying to access the system, and all the available capacity is used up. Then you will have some call blocking. Okay, and this is called a blocking system. Okay, so this is an example that will you know uh, give you a perspective. Okay, so let's say you have this number of channels. Okay, 1 2 3 up to 10. So you have 10 channels, and the red lines shows the occupancy of these channels in minutes. Okay, so let's say from 0 to 60 minutes, okay, this channel is occupied a total of 51 minutes. Okay, so let's say this is 2 minutes. Okay, this is again 3 minutes. Okay, this is again 1 2 3 and half, so 3.5 minutes. In this way, if you count the duration of all these red lines actually signify the number of minutes a call is in progress. So the total call occupancy time for this channel 1 is 51 minutes. Okay, and the total number of calls is 70. So this is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 and 17. So these are the total number of calls. So in this way, every channel, you can see they have some occupancy for certain duration of time, and then the channel is idle. So in this second channel, you have 47 minutes of total call occupancy time, and total 16 calls are there. Okay, so these channels are very highly occupied, and actually, so out of 60 minutes, 51 minutes are occupied, 47 minutes are occupied, as compared to, let's say, this case where the channel is only occupied for 6 minutes and there are only 2 calls that were there, and the remaining of the channel is empty here. Okay, so there are a lot of empty slots here. Okay, so if you count the total time for all the channels, then you can see that there are 294 minutes of call occupancy for these 10 channels. Okay, and there are total 97 calls that has happened. Okay, so if you try to find out the rate of calls per minute, rate of calls per minute, and if you call this as lambda, okay, so this is basically your 97 divided by 60. Okay, and if you define another term called H, which is the average, okay, holding time per call, okay, average holding time per call in minutes, then this will be the total number of minutes divided by number of calls. Okay, so this will be 294 divided by 97. Okay, so therefore the total traffic, okay, the total traffic occupied, okay, by this 10 channels, okay, is given by A equal to lambda times H. Okay, and this is basically, if you do the math here, this will be 294 divided by 60. So this will be 4.9, and the unit of the traffic is called Erlangs. Okay, so this is named after a famous engineer called Erlang. So 4.9 Erlang. Okay, so now let's say if all the channels, okay, all the 10 channels are occupied for all the 60 minutes. Okay, so what would have been the total number of calls? Okay, so that will be uh, 600. Okay, let's say there is a one call, okay, one single call that is occupied for the entire 60 minutes, and that happens for all the channels. Okay, let's say, okay, in that case all the 10 channels will be occupied for 60 minutes, so all these numbers will be 60. Okay, let's say, and this 294 will become 600 because there are 10 channels and all of them are occupied for 60 minutes. And let's say there is a one call, okay, for the entire 60 minutes in all the 10 channels, so this will be 10. Okay, so in that case your rate of calls per minute would have been 10 by 60. Okay, and your average holding time per call in minutes would have been 600, okay, divided by 10, and that will be 60. So for 60 minutes all the channels are occupied. Okay, so this would have been, if this was the case, then this would have been, okay, let me write with a different color here. So then this would have been 600 by 10. Okay, so that will be 60, and then this term, the total traffic, okay, would be lambda times h, and this would be 600 divided by 60. Okay, so this would have been 600 divided by 60 if all the channels were occupied entirely for 60 minutes by a single call. Okay, so then this will be 10. Okay, Erlang, and that is the total, or that is the maximum capacity that you can occupy. Okay, because there are 10 channels, and if all of them are fully occupied, then you will get 10 Erlangs of traffic. Okay, and that would be the case if there was a one single call that would exist for the entire 60 minutes of observation in each of these channels. Okay, but for this particular example we have 4.9 Erlang, so this is basically 49% occupancy of the maximum available occupancy. Okay, so there are a lot of system performance questions that you might ask yourself. Okay, so what is the probability that a call request is blocked? What capacity is needed to achieve a certain upper bound on probability of blocking? What is the average delay? What capacity is needed to achieve a certain average delay? And to answer all these questions, okay, you need to model the system mathematically. So the first term that you should appreciate for that modeling is the load presented to the system, or the traffic intensity, and that is given by lambda times h, as we just discussed in the previous example here. Okay, so lambda is the mean rate of calls attempted per unit time, and h is the mean holding time per successful call. So we calculated this term, so we had lambda here and we also had h here. Okay, we defined it with capital H, but you can define it with small h as well, and then we said that the total traffic intensity was lambda times h. Okay, so this is the load presented to the system A, and this actually is the average number of calls arriving during average holding time for normalized lambda. Okay, so A equal to lambda times h. And now that if you obtain A, okay, then you can use that A that you calculated using lambda and h to calculate the probability of blocking. Okay, so before calculating the probability of blocking, you should assume that what type of system that you are looking into. Okay, you can have a system where lost calls are delayed. Okay, so in this case your blocked calls are put in a queue awaiting a free channel, or you can have blocked calls rejected and dropped. So you can have LCC system where your lost calls are cleared. So in this case your user awaits before another attempt, or your user repeatedly attempts calling, which is called lost calls held. And then you have to also determine whether the number of users is assumed to be finite or infinite. Okay, so based on all these factors, whether it's a lost call delayed assumption or a lost called cleared assumption or a lost called held assumption, and whether your number of users is finite or infinite, you can define your probability of blocking in terms of your A, which you calculated as lambda times h, and the total number of servers n. Okay, so for example, if you assume infinite source and a lost call clear system, then your probability of blocking P is given by this formula. Okay, so this is basically the probability of blocking, sometimes also called grade of service. Okay, and this formula is valid when you assume infinite source and lost called cleared system. So infinite source means the number of users is assumed to be infinite. Okay, so this is also called Erlang B formula. Okay, and this is a famous formula that is used in modeling the traffic and its relationship with the probability of blocking in a cellular mobile network, where you are assuming that your lost calls are cleared and the number of users are infinite. Okay, so we will study more of this formula and see how to apply this for cellular network design in the next lectures that are coming up. Okay, so for this one we will stop here, and I will see you in the next video lecture. Thank you.